Okay, so thank you very much for the invitation. So I will present a joint work with Nicolas Vichery. Please, Viterbo invariants. So as they are defined for, say, cotangent of some manifold. So they are defined in greater generality using Fourier theory, but let us assume that the lambda are which is quadratic at infinity, and we take some cohomology class alpha in the base M, and the cohomology of the base can be identified with the relative cohomology of the level sets of the generating function, say between minus infinity and plus infinity, so written here, less than t0 or minus t0, up to a shift by the index of the quadratic function at infinity. So we choose some class, and the spectral invariant of alpha is defined to be the sub of the value t, such that the restriction of alpha level f less than t is equal to 0. A number for each cohomology class in M. Excuse me, 1 minute, 1 minute, okay. And the color is about a bound for this invariant. And what I will prove today is the following. So if we suppose as some metric, and lambda is contained in the unit ball bundle, so not only in T star M, but in the unit ball bundle in T star M. We prove, okay, well, in the case where M is a quotient by the quotient of a compact Lie group by some subgroup. And it says the following: if we consider maximum and minimum value of this C alpha, so I should write here C plus is the maximum of the C alpha, and it corresponds to the fundamental class of M. And C minus corresponds to the class of identity, and at 1, and the maximum and the minimum is bounded here by more or less a dimension of times the diameter plus factor 2. For the case M is a compact Lie group, and when M is a kind of bound, we multiply by the dimension of the base, so the dimension of M, plus 3 to the square. Okay, that's so it's about to bound the differences between the spectral invariants. So it was indeed conjectured by Viterbo in the case equals the torus. This question was in relation with symplectic homogenization. So yes, you need to study the spectral invariance of some isotopy of the zero section by multiple composition of some Hamiltonian isotopies. So we phi here is some Hamiltonian isotope, try to some power and look at the image of the zero section and take the value. And in homogenization, it is useful to understand the behavior of this C plus or C minus. Okay. But and second, almost very important, this theorem is not proved by Shirukin 2 years ago in 2 papers. The first one where he proved the case of M to be some symmetric spaces of the spaces on R, C, and H, and also the sphere. So of course these one are also compact group. And the case of where M, so this is much more general, where M is a string which is of the action of the loop space of the cohomology of the loop space of M onto the cohomology of M by a Chasles-Sullivan product. I should also note that in the case M is a projective space or the sphere, the statement of Shirukin it's much better in the sense that the constant which bounds this spectral invariant it's much better. Let's say linear in the dimension. Okay, and we also have recent results by which bounds the spectral invariance in terms of the boundary lengths between lambda and the zero section. In fact, no, excuse me, not lambda and the zero section, but lambda and the fiber at some point. The bound we give in the previous slides are also holds for not only for the differences between spectral invariants, but also for the boundary lengths. So I will come back to this in 2 slides. It bounds also the boundary lengths between lambda and the zero section. And we have also an example by showing that the condition that lambda is an embedded submanifold of T star M is necessary. If he gives example where lambda is only immersed and the spectral invariant not. Okay, so I don't know if there are questions. I hope you can hear me now. I have no idea of. Okay, or good. Good. Okay, so I will.
We can hear you finally out, but it may be that it's because of your browser. That's what Denis is suggesting.
Excuse me, that.
What browser are you using?
Denis says it's good.
Firefox.
Sometimes Chrome is better, but let's.
Well, okay, then I don't have it on my computer. Sorry.
Oh, okay. Then it's fine. Let's just keep going. It's good enough.
So I will explain the proof in the talk, and the proof relies. So it's very different from the weekend, and it uses support by Kashua and Shapira in the 80s. First, recall what it is. So we will use the graph category of sheaves on Herm. And maybe what I should say first. So the typical sheaf first is the example given just to some closed subset, say Z. And for a closed subset like this, we define the constant sheaf on Z denoted kz. So k here is a coefficient ring, but here it will be a field. So we define the constant sheaf kz on Z by its section on some open set U by saying that it's just the set vector space of function on U intersects D with value in K, which are locally constant. So I mean just constant on each connected component of U intersect Z. So it's just K K power pi 0 of U intersect Z. So this is our typical sheaf in this. All other are made by operation like transfer product, direct images, or some, well, essentially this operation. But otherwise, I will not recall explicitly what a sheaf is. So a sheaf is a data of a K vector space for each open set of M. So M is our which satisfies restriction properties and growing properties. But the typical example here is this constant sheaf Kz, which I just defined. Okay, for a general sheaf, Kashiwa introduced some subset of T star M, which is closed, conic for the action of R of, multiplication by a positive number, the fibers. So it's, you can think of it as rather as a subset of the sphere bundle, or of the co-sphere bundle. And it is not directly related with symplectic symmetry, but there is a theorem which says that this microsupport is always co-isotropic. In fact, we will consider the case where, in general, it is, for general sheaf, it is co-isotropic in some sense. I will not give the definition, but almost. What I give is a property which looks like, in this case, and in fact, it is a global version of the definition. So, what is the use of this microsupport? It says something on the cohomology of the sheaf. So recall that if you have a sheaf on some manifold, you can consider its cohomology over any open subset of the manifold. And typically, Kz that I just defined, the cohomology of Kz over U will be, in fact, just the cohomology of U intersect Z. So it's very to understand in this case. But anyway, we have some cohomology groups associated with F. And the question that they consider is, you deform the open set. What happens to the cohomology? And the microsupport is introduced to say that in some cases, cohomology does not change. So more wisely, let us consider some function phi on M. So our sheaf is defined on a manifold M. Take M with some properties, say it is proper. And we consider two values S and T. Assume that the differential of phi, d phi x, does not belong to our microsupport. So recall the microsupport is a subset of T star M. So we assume that d phi belongs to the microsupport for all x such that phi of x is between S and T. And we consider the restriction map from the cohomology of F on the level phi less than T to the level set phi less than S. And with our hypothesis that d phi does not meet microsupport, this restriction isomorphism. So that's I think the first main property of the microsupport, and in some sense, the definition is a local version of this property. I give a picture just below. So here, Z is a closed set, so above some line, some curve in R2. So I just define the constant sheaf on Z. So I give a picture of the microsupport sheaf on Z. So it consists of over Z, and on the boundary, it is given by, well, say Z has a smooth boundary, and Z is defined by I greater than 0. Then the microsupport is half of the conormal bundle of the boundary. Or more precisely, the half given by the positive multiple of deep psi deep psi along the boundary. So it's picture with the blue arrow here. And what is the meaning of the propagation lemma? It says that if we start with a small ball outside Z, so the cohomology is 0 here, and we increase the ball, then when we meet the boundary of Z, the cohomology will be K. And in the opposite direction, suppose you start with a small ball inside Z, and you increase the ball, then you also make Z in something, and the cohomology. So here at the boundary, in fact, d phi. So if the open set is d phi like something, is opposite to deep psi. It's not does not quite. Okay, so I hope this gives a picture of what is the microsupport. And here is a more quantitative version, which will be useful in this talk. Now we consider sheaf not on M, but on M times R, which is, in fact, we will consider sheaf as related to the wavefront of our lambda seen as a Lagrangian in J1M. Suppose you put some metric on M, a cone in the cotangent bundle T star of M times R. And it is a cone given by the set of xt psi tau with tau bigger than tau bigger than a multiple of the norm of with respect to this metric. And we define a kind of dual to this. This C prime alpha R is a kind of cone in M times R, which is in some sense the polar set of this cone in the cotangent bundle. So it is pictured on the side, and is given as a set of xt with t less than minus the distance of x to some fixed point x0. And we do this only for x not too far away from x0. Say distance of x from x0 is also less than r, where r here is less than the injectivity radius of M1. What I claim is that if I consider the restriction from the cohomology of F above this kind of cone in M times R, the cohomology of F restricted on the line x0 times R over the open set x0 times minus infinity 0, then this is an isomorphism. Sense, with some assumption on the microsupport, we will extend cohomology classes on F defined on some line to cohomology classes for some bigger open sets around this line. Okay, so that's a quick course on sheaves on micro supports. And now, what is the link with symplectic geometry? So maybe what I explained here relies on some ideas introduced by Tamarkin, which made the link between symplectic geometry and sheaves precisely in this way. We consider again our compact exact Lagrangian lambda and T star M. So we turn it in a conic Lagrangian. So we call that the microsupport is always conic. So we turn it in a Lagrangian, or if you prefer, in a Legendre in the one jet space of M. So say lambda prime is contained in T star M times R. And we have a theorem which says the following. The unique sheaf F0 on this product, M times R, such that its microsupport is equal to lambda prime, say outside the zero section. Let us forget the zero section here in this talk. With the property that at infinity, so F0 restricted to M times T for some fixed T, T going to minus infinity, here is 0, and in restriction at plus infinity is a constant sheaf from M. So there exists a unique 0 with these properties, and moreover, all sheaves on M times R satisfying this first property, I mean microsupport is lambda prime and it is 0 at minus infinity, are product of this F0 with some locally constant sheaf. Okay, so I proved this some years ago, and we also have a proof, a more recent proof by Chandler, certainly better, in fact. And both proofs use only micro-local sheaves method. And an interesting point is we also have another proof by Viterbo, which use theory, and which expresses the germ of F along a line x0 times R as the Floer homology between and the cotangent fiber at x0. And more precisely, the value of T, which makes sense here, corresponds to the filtration on this formula. And again, to make the link with the definition I gave in the beginning, if lambda has some generating function, then F0 is very simple to define. We just consider the map for M times R n plus 1 to M times R, so forgetting the extra variable Rn. We start with the constant sheaf above the graph of F, so constant sheaf on T greater than, and we take its direct image to M times R. And this is our F0. Okay. And now it's not difficult to understand what the spectral invariants are in this framework. So again, it considers this lambda and lambda prime, which is the conified version of lambda. So lambda prime is defined using some, yes, I didn't say that, but to define lambda prime, you choose a primitive of the Liouville form restricted to lambda. It gives you the variable R on n times R. And now, if you want to understand the spectrum, you take this sheaf F0 to on M times R, and you project on R. So this gives you a sheaf on R. Now a sheaf on R, we say it is constructible, which is the case if lambda prime is generic enough. So for reasonable sheaves, we can understand a sheaf on R trivial representation of type AN. And Gabriel says that our sheaves, if K is a field, our sheaf is decomposed as a sum of constant sheaves, and these intervals are of the type C plus infinity closed, or AB bounded, which are closed on A and open on the side B. And well, in fact, sheaves on R have now a new name. They are called persistence module, and these intervals here are barcodes. Now, you can understand from the previous slide that F0 was just the direct image of the constant sheaf determined by generating function. The split with the CI which appear in this decomposition. So the next, so here I give a picture in the most simple. We have a swallow tail on the cylinder with a maximum and a minimum, and when we project on R, we have two infinite bars on the interval C plus and C minus plus infinity. So the next slide is more or less the same, still in dimension 1. But now I consider a line which is almost the zero section everywhere, except that it is pillaring for some time around 0. Then the corresponding front is a series of, say, nested swallowtails. And if we project to R, what we get here is one infinite bar, which correspond to minimal point, and some finite intervals, but all these intervals are bounded by the area of the circle. I mean, if I am spiraling inside some circle, this gives a bound for the length of the barcodes. But the barcodes are not bounded themselves. I mean, they are all of the type A. So B minus A is bounded, but E and B are not bounded. Okay. That was for the spectral invariant. Okay. And now, so I said that this kind of, I mean, this way of making a link between sheaves and symplectic geometry was, so there is another interpretation given by Nadler-Zaslow, but so not so straightforward as Tamarkin's interpretation. But still, in this framework, Tamarkin gives a way to understand the filtration on the Floer complex, or maybe better to understand the action, or to understand what is the Novikov ring in this framework. And it does this as follows. So a remark, so this is not very difficult, but it's a remark. All the sheaves that we consider here comes with virtual morphism from the sheaf itself, F, to its translation, its vertical translation by any positive number D. So TD here is the variable T. And we have a morphism from F to the direct image of F by this TD, which is called tau D by Tamarkin. So in D equals 0, of course, quantity, And this tau 0 is nothing but the identity morphism. And another point, which is important for the rest of the talk, this 2D, which is a morphism, can be interpreted as a section of some sheaf. Well, this is not surprising. A usual morphism of sheaf can be interpreted as a section of the Ohm sheaf. So we have some internal Ohm in the category of sheaves. And the morphism of sheaves is a section of on this internal Ohm. So Tamarkin also internal Ohm in some quotient of the category of sheaves. And with the property that a morphism to TD star F prime. No, so now we have two sheaves F and F prime, and we translate the second one. So this Ohm between F and TD star F prime can be as a section of some other sheaf Ohm star over n times an interval ending at minus t. So n times minus infinity minus t. Okay, so below I give a definition of this Ohm star. So it's very simple with respect to usual sheaf operation, but if you are not to sheaves, it's not so important. And maybe just to say what we are saying in the simplest case. So suppose M is a point, so we consider R sheaf on some interval. If we take its direct image by TD, it's a constant sheaf on the same interval translated by D. And if you remember the definition of the constant sheaf on a closed set, it was given as a space of function on U intersect the closed set, if U is some open set. And of course, you have natural restriction morphism. I mean, if a closed set Z prime is contained in another one Z, a natural restriction morphism for KZ to KZ prime. And this is the case here when D is non-negative. And something important here too is that if we consider tau D for a constant sheaf on some finite interval, of course, as soon as this interval will be disjoint, I mean, I start with constant sheaf on A, as translated by D. So for D bigger than B minus A, of course, it will be separated. And this morphism tau D will vanish. And that's the way we will use this Ohm star to reinterpret the spectral invariant. So let us make some computation on R first. So recall that we have this sheaf F0 on M times R associated with lambda. Take this direct image on R to obtain the barcodes. So let us make the computation just for barcodes. So we are on R, and we consider Ohm star of the constant sheaf on C plus infinity to the constant sheaf on C prime plus infinity. So we take bar, and what we get is the constant sheaf on minus infinity, C prime minus C. And we have a similar computation for finite bars. The point is that the Ohm star from KAB to itself is the sum of two constant sheaf, one on A minus B0 on the constant sheaf on the interval A minus B, the next one on 0 B minus A. The point is that if we only consider what is above 0 on R, and we cut by 0 plus infinity, so this is the meaning of this R gamma 0 plus infinity, just mean first restrict to 0 plus infinity, and then takes the direct image back to R. So this is still a sheaf on R. So if we, so to summarize what we have seen up to now, if we start with this F0, which is associated with lambda, we take its direct image to R, and we take the Ohm star with itself and cut above 0. What we get is a constant, is a sheaf which is decomposed as constant sheaf on some intervals plus in the cohomological degree. And these intervals are all finite of lengths. I mean, between these intervals, we have some of them gives which are whose length is the differences between the spectral invariants. And also we see the length of finite barcodes appearing there, but it was not. So in particular, the remark here is that if we can prove that 2D of this here, so we take Ohm star of direct images of sheaves on R, cut above 0 plus infinity. Suppose you can prove that 2D of this sheaf vanishes from D, then it gives you a bound for all the lengths of this interval G prime K, hence for all the differences between spectral invariants. Okay, and this is precisely the statement of the next slide. So first, we consider the case of a compact Lie group G, and we consider the sheaf just written before, but instead of just F0 on itself, take two sheaves F1 and F2 with microsupport lambda prime. The reason we take 2 and not just F0 is to be able to apply this to get the case of some homogeneous space. Okay, so the statement is precisely that the morphism tau D of this sheaf, this is a sheaf on R. And the morphism tau D of this sheaf vanishes for D bigger than some bound. I mean, just the dimension of the group plus times the diameter times 2. Okay, so in particular, this theorem gives the first statement in the first slide. So it gives you the conjecture for Lie group. I will now explain it. It's quite simple, in fact, with the that we have seen already.
May I ask a question?
Yes.
Can you recall what was tau D?
Yes. So I go back to the maybe yes. I comment here. So this tau D. So it's a natural morphism defined by Tamarkin for any sheaf on M times R with microsupport. So here, maybe should say that. So tau is the fiber variable on T star R, and we assume that our microsupport is contained in positive. So T and tau are the variable on T star R. So for any sheaf with this kind, we have natural morphism. And this morphism, say in the simple case, we just take M as a point. So I recall, suppose we consider the constant sheaf on some finite bar. So K is infinity. We translate this this sheaf by this translation TD. So what we get is a constant sheaf on the bar translated. And now we have a morphism, a very natural one. So recall that the section of our sheaf on some open set U is a set of functions from U intersect our interval K, which are locally constant. Just because they are function and U intersects the interval, of course we have a rotation map from the constant sheaf on C infinity to the constant sheaf on C plus D infinity. Of course, if D is non-negative, we just restrict our function to U intersect C plus D plus infinity. So that's our morphism Topology. So it's very simple, in fact.
If you think in terms of persistent modules, which you may or may not.
Excuse me?
If you think in terms of persistence modules, which some people may want,
yes,
some may not want, it's just the standard map between the.
Yes, I guess so. Yes, yes, it's very standard in terms of barcodes. But the point is that the same morphism is defined not only on R but on M times R as soon as the microsupport is oriented in the positive direction. So I could give the same definition. So if we go back to the picture that I have on the second side, where I draw Z, which is the constant sheaf above some line in R2. So you see that in this, if I translate Z in the vertical direction, then the translation of Z will be contained in Z. And I will have the same restriction map. So that's the morphism 2D. Well, of course, it is easily described when we consider just constant sheaf on intervals or on closed set. But of course, the general sheaf can be a bit more complicated. Still, if we consider constructible sheaves, they are made of building blocks which are constant sheaf on locally closed subset, and on each block it is interpreted in this way. This morphism 2D. So recall, here I'm back to the theorem. So recall from the previous slide that what we want to understand is 0, so this tau identity morphism. And the question is, we increase D, and the question is when tau D becomes 0, when tau D vanishes for D being. And the point is that by the remarks, the computation we made on R, the vanishing will happen when D is bigger than the length of all the intervals that we have in our computation. So in particular, it will be bigger than the differences of spectral invariants. So the theorem which is stated here implies the conjecture for a compact Lie group. And the idea is quite simple. So the plan with this Ohm sheaf on R is that we started by projecting F0. So F0 was a sheaf on M times R with some microsupport. We project it on R. So of course, after projection, we have no information on the microsupport. What we'll do is to reinterpret R as the average on some other Ohm star, but defined on G times R. And it will be some Ohm star between F1 and the image of F2 by the action. So here mu G is the action of an element of the group. And consider the average star for all G. So maybe I should better. say more precisely what I mean by that. So consider on G times R square 3 projection and define arm star adapted to our group. So it's the same definition as the marking that I recalled quickly before, but on G times R. So on G times R, I have 3 natural maps which are 2 projections to G times R, and also the action. And I pull back F2 by the action. I pull back F1 by the second projection. Push on between the two and pull back by the first projection. So this gives the sheaves on G times R. And now using some very standard formulas of sheaves, because that if we project again this sheaf on R, so our map A is a projection to R, we find exactly the arm star we are interested in. Okay, but the point that R is a sheaf on G times R, and maybe we can say something on this micro support which is interesting. So first, yes, as we get above 0 infinity, so say define K to be the cutoff of this arm star G above or on G times 0 infinity. So what we want to understand is tau D of K.
What is K? K is on the line.
Can you hear me?
Yes.
I'm saying I'm almost out of time, but I give a last slide very quickly. So what are the properties?
You can certainly take 5 more minutes because we took some time in the beginning to start. So you can certainly take your time, 5 minutes, no problem. Okay.
So I explain very quickly what are the ideas. So we define this sheaf K. So we have this arm star G, which is the definition of the marking. But now it's achieved on G times R. And we cut above 0 infinity. We call this K. So what are the properties of this K? So first, we can very well understand its relation to the line E times R. So E is, of course, the identity of G. And it gives you 1 on just the translation of F2. So E doesn't act on G. So this mu G inverse just becomes a translation. Using just usual properties of the micro support, like the propagation on things of this kind, we see that this restriction to E times R will in fact be constant for it will be constant on E times minus infinity, on E times 0 infinity. So except the point 0, it will be constant. And you can easily compute what it is at minus infinity and prove that in fact our sheaf K restricted on the line E times R is actually 0. And now we can also easily bound the micro support of our sheaf K just by natural bound associated with sheaf operation. And what we find, starting with the fact that lambda is contained in some ball bundle, we can bound the micro support of arm star to itself by some cone. As in the slide about the propagation of the cohomology. And now using the fact that K restricted on the line is 0, the fact that we can bound the micro support by a cone, we can deduce the vanishing or using propagation or the section of this K to K on some set. And precisely, you can prove that the 2D, so we call 2D is a section of this Ohm star. So 2D, basically a ball diameter R around the identity is if D is twice the radius of the ball. So this gives a vanishing of this 2D for small balls. And then using a triangulation of G and some induction, some excision distinguished triangle for sheaves, we'll be able to deduce a vanishing of 2D over the whole group. Okay, this is a very simple proof using standard sheaf properties with standard property of the microsupport with sheaf operation. And if I have 2 minutes more, I explain how to deduce the case of the quotient. Very quick. So the statement of the, so now we consider M is the quotient of the group. So the statement is the same, except that the bound is not as good. There is this M plus V square in addition. And the idea is not so difficult. We go back to the previous theorem by taking the inverse image by the quotient map. So let Q be the quotient map from G to M and make the product with R. So now you have sheaves on M times R. Take the pullback. You have a sheaf on G times R. And you can apply the previous theorem on G times R. So the problem is the following. It's not difficult to see that the spectral norm of the natural inverse, so lambda now is in T star M. You take its pullback in T star G, and you have a natural bound for the spectral invariant, but not in the good direction. So what we can prove is we can bound the spectral invariant for the direct image of our invert image. I mean, the sheaf Q star of Q inverse F. So this is not what we want. We want F, of course. But it's not so difficult to understand what is the direct image. It's just F tensor by some locally constant sheaf, which is the direct image of the constant sheaf on G on M. I mean, we take the constant sheaf on G and take the direct image on M. And now we have just a which is not so difficult, which says that up to taking some iterated counts starting from L, we can exhibit the constant sheaf of some iterated cone of L. And we can bound the number of steps that we need and deduce a bound also in the case of a quotient. I am out of time, so sorry. I will stop here.
Thank you very much. Questions? Claude.
Yes, in fact, I had a proof of this, but it's not completely written down using generating functions, which is probably not surprising. But what I think one can prove is that if you have a map from a closed manifold to the diffeomorphism of M, which is essential in the sense that the pullback of the fundamental class of M is not zero, then you have some bound. Is that also true in your case?
Yeah, so indeed. So here, if so indeed the point in general, the pullback of so consider S3 mapping to S2.
It works for G over, yeah, it works for G over H, but I guess.
You mean, if I pull back to S3, it be 0. Or it depends what kind of pullback, but.
Sorry, I didn't hear what you said.
It means that all the inequality here is an equality.
So this is usually an inequality, yes.
Yes, okay. So in general, the problem is to say so vector class of M will can be 0 in the cohomology of G. If it is not the case, indeed, we get the result directly. And the trick here is, so it works for a sheaf of the type direct image of inverse image. And the point is that we can the sheaf F itself by taking iterations of this kind.
I'm missing some words.
Excuse me?
I missed some of the words that you said, but I guess the answer was essentially yes.
Yes.
Okay. Yes. And another
I
remark
mean,
is
essentially up to the fact that we have to take some sequence of cones starting for the sheaves given by the case of the group to get the sheaf we are interested in. And this sequence of cones will give a less good bound for the spectral invariant. So each time we take a cone to add some number.
I don't think the value of the constant is that important for the moment, at least. And the other thing is that I guess you only need that lambda is an exact Lagrangian. You don't need that it's isotopic to the zero section, which I think was assumed by Sheluki.
No, not in the second paper.
Not in the second paper. Okay, yes.
No.
If not, let us take the speaker again.